Okay, now we will discuss this particular topic, which is to obtain the expression for the torque experienced by an electric dipole under the influence of uniform electric field. Uniform electric field. What it means is, in a given region, if the electric field at any point in that region is having the same magnitude and same direction, then that electric field may be termed as uniform electric field. And diagrammatically, it is represented by a set of equidistant parallel lines. This is the symbolic representation of uniform electric field, right? So suppose a dipole you all are aware, it's a system comprising of two equal and opposite charges separated by a finite separation. That's an electric dipole. So suppose this is the center of the dipole and this dipole is placed under the influence of this uniform electric field. This is the dipole length, the distance between these two equal and opposite charges 2a. This is the center of the dipole, so this is a, this is a. Dipole length, dipole moment, the vector quantity, you are aware, they are directed from negative charge to positive charge. This is p vector, this is the dipole moment. This is the angle between the dipole moment and the electric field. Let us consider it to be theta. So theta is the angle which the electric dipole moment of the electric dipole makes with the electric field, right? Now, before we proceed, we need to understand a few basic facts which we have studied earlier. Now, electric field, as you are aware, it is actually given by limit Q0 tends to 0. It simply suggests that the test charge under consideration should be having vanishingly small magnitude, so that it do not alter the position of the source charge. It can't be 0. It should have vanishingly or infinitesimally small magnitude. So, whatever electric force is experienced by this test charge divided by its magnitude, that gives the strength of the electric field. So, basically, electric force experienced by this charge under the influence of this field would be Q0, right? This is the formula which we will be using over here. In case it is positive, then F vector would be equal to Q0 E vector. In that case, it will experience force along the direction of the electric field. That is, F vector is parallel to E vector, right? In case the test charge is negative, then F vector would be minus Q0 E vector. That is, in this case also it will experience the same electrostatic force having same magnitude but opposite directed. In this case, F vector and E vector, they are opposite directed. Negative charge will experience an electric force in a direction opposite to that of the applied field. So here the applied field, this is the uniform electric, this is due to some other source charge, and these two charges can be considered to be the test charge. Now this is positive charge. As per this, it will experience force QE along the direction of the electric field. This is positive charge. So it will experience force QE along the direction of the electric field. While this is negative charge, it will experience the same force but in the opposite direction. Negative charge experiences force in a direction opposite to that of the electric field. So over here, it will be like this. Same magnitude, both the forces are of equal magnitude but opposite directed. And their lines of action are also different. This force is acting along this line, while this force is acting along this line. So they have different lines of action. So you are aware of the very basic concept. Whenever a body is under the influence of two equal and opposite forces which are having different lines of action, then they will constitute a torque. Like in this case, these two forces are equal in magnitude, opposite directed, and most importantly, their lines of action are different. So obviously they will constitute a torque, and as a result, this torque, as you are aware, it induces rotational effect. So it will tend to rotate the dipole about point O in the clockwise direction. That is, along the direction of the electric field. Suppose this is the dipole, this is the positive charge, it experiences a force along this direction. This is the negative charge, it will experience a force in the opposite direction to that of the electric field. So it will experience a torque. So it will tend to rotate in the clockwise direction and will tend to align along the direction of the electric field. Right? So these two forces will constitute torque. Torque, mathematically we are aware, it's given by product of magnitude of either of these two charges. That is QE. It is given by the product of magnitude of either of the forces and the perpendicular distance between them. These are the two forces, anti-parallel, so the perpendicular distance between them can be considered to be small letter d. So this is the formula for the torque. Torque is given by product of the magnitude of either of the force and the perpendicular distance between them. Now, this angle is also theta, corresponding angle. This is a right angle triangle. If you consider sine theta, it will be perpendicular by hypotenuse. D divided by this hypotenuse is the dipole length 2a. So D can be written as 2a. So substituting the value of D over here, we can write Q 2a E sine theta. Simply substitute the value of D over here as 2a sine theta. Now there is a special term, we are aware of it. It's known as electric dipole moment, represented by small letter p. So torque, it is equal to Pe sine theta. So this is the magnitude of the torque experienced by an electric dipole under the influence of uniform electric field. Theta, remember, it's the angle between the dipole moment and the electric field. Torque is a vector quantity, so it can be represented in vector manner like this. It can be given by the vector product of the dipole moment and the electric field vector. Now, using the properties of the vector product, we can safely conclude that torque is perpendicular to P vector as well as it is perpendicular to E vector. Now, what about the direction of torque? We have derived the expression for its magnitude. What about its direction? We are aware, if a vector is given by the cross product of two another vectors, then its direction is given by thumb rule. So, P cross E, this is P vector, this is E vector. So, like this, make use of thumb rule. The rest of the fingers should orient or should align along the direction of measurement of the angle. Orientation of the angle is from P to E, like this. So, let's make use of this rule. So, in this case, thumb will represent the direction of torque. So, the direction of the torque is perpendicular to the plane of the white board, which contains P vector as well as E vector and directed inwards. So, the direction of torque is perpendicular to both P vector as well as E vector, or in other words, the direction of torque is perpendicular to the plane containing P vector and E vector and directed inwards. So, that's the direction of torque. Now, let's discuss some special cases as well. First case is, suppose the dipole is lying along the direction of the electric field. So, obviously in this case theta is 0. In case theta becomes 0, sine 0 is 0, so torque is 0. So, if the dipole is aligned along the direction of the electric field, it won't experience any torque, right? Let's consider another case. Suppose this is electric dipole and this is electric field. So, what's the angle between these two? They are anti-parallel. So, it is 180 degree. Again, sine 180 degree is 0. So, tau is equal to 0. So, again, very important conclusion. If the dipole is aligned along or opposite of the direction of the electric field, then it won't experience any torque. In both the cases, the torque experienced by the dipole is 0. So, the question arises when it will experience maximum torque. So, for that, sin theta needs to be maximum. And for the value of sin theta to be 1, theta should be 90 degree. So, that's case 3. If theta is equal to 90 degree, then tau is equal to tau max and it will be equal to P. And this is only possible when dipole is aligned or placed at right angle or perpendicular to the direction of the electric field. So this was the article regarding the torque experienced by an electric dipole under the influence of uniform electric field.